Hey Math 8 students, so today we're going to be going further into our geometry kind of exploration in the coordinate planes. We're going to look at concept of dilations and similarity. So learning goals for this week, we want to make sure that we know what a dilation is and how it can scale geometric shapes up and down. We want to know how to implement and recognize when a dilation happens in a coordinate plane. We also want to understand that dilations create something called similar figures. So a little bit different than congruent, but we'll look at that in a little bit. So let's start with that exploration problem that I gave you last Friday. So you haven't done that yet, go ahead and pause the video, do that now, because that's what we're going to use to kind of jump off into this concept. So we've got this triangle here, and it looks like it's a small splash pad, and we're representing it with this triangle here, ABC. And this architect wants to scale up this splash pad, so they want to make it larger. And so they've scaled it up to this triangle ADE. And we're going to look at kind of the similarity and differences of it to see. So probably what you found is if we look at this, that triangle ADE is quite a bit different in size. However, though, they're pretty similar in terms of their shape, because if we look at this, well, there's a right angle here in both of these triangles. If we look this angle at vertice B and vertice D, these angles are exactly the same. They open the same exact angle measurement. And we can say that this angle here at vertice C and vertice E, these are equal as well. So they have same angles. And if we were to scale it up, like if we were to look at this, if we were to about a little bit more than double this side length, AB to AD, to AC, AE, and we kind of doubled both, maybe a little bit more than doubled about this. So another thing that it's like is they're really the same scale. And if I were to take this, I could even scale this up and say, well, if I just made this triangle just bigger in all the same directions, we'd have the same shape. So what we call these are similar. And the way they became similar was just a dilation. So a dilation scaled it up and down. So essentially, we're just dilating an object to create something that's the same shape, but it's a different size. So we're scaling it up and down. So let's take a look. I know it's towards the end of the year, so I'm going to try to make my videos a little more bite-sized, but we're going to take a look at what this looks like in a coordinate plane. So I'm going to take an object and I'm going to dilate it in the coordinate plane, and that's going to create a similar figure. So remember, similar figure, we said same shape, different size. So our task here is we're going to dilate the geometric figure ABCD by a factor of 3. So that's essentially the same thing as saying, let's triple it in size. But we want the same exact dimensions. All right, so in this case, we're going to have kind of a step-by-step. It's not that hard to do this, but essentially we're going to take each distance from the origin here, and we're going to triple it. So step by step, we'll just start by writing down our vertices. So I've got the A vertice, that's at 1, 1, we'll write that. I've got the B vertice, I've got 1, 3. C, if we do that, it's 3 over 3 up, and D looks like it's 3 over 1 up, so 3, 1. So all we're going to do here, and first I'm going to try to illustrate it real quickly, but all I'm going to do is I'm going to take the distance from the origin, I'm going to triple it. So for instance, if I wanted to get the dilated vertice for B by a factor of 3, I would just take this line and I would triple it in length to get about there. So we'll see what that looks like. Let's take vertice B, let's triple it. So We'll go ahead and draw this in a different pen real quick. So I'm just going to multiply each coordinate by the scaling factor. So here, if we want to get b prime from b, we're just going to triple its length. So I'm going to take b, I'm going to multiply its coordinates by 3. So b prime, multiply the 1 by the 3, I get 3. Multiply by 3 by the 3, I get 9. So you'll notice I just took this arrow here and I tripled it in length. So b prime would go right here. And now I just do that with all the coordinates to dilate it. So a prime, 1 times 3 is 3. 1 times 3 again is 3. And we get a prime is right next to c. And c, we multiply by 3. So 3 times 3 is 9. 3 times 3 is 9 again. And we go over here to 9 comma 9. And we got c prime. D prime, do the same thing with coordinate d. 3 times 3, that's 9. 1 times 3, that's 3. And we'll go to 9 comma 3 for d prime. And you'll see here, if I look at this, I've got a geometric shape that has the exact same angles to it. However, let's see if I can fix. I'll just draw these by hand. My arrow tool isn't quite working, right? That's okay. So if I look at this, I've got a shape that is 3 times in size. So it's dilated by a factor of 3. So here we've got dimensions of 2, 2, 2, 2, just a sort of basic 2 by 2 square, where here we've dilated it to a 6 by 6 square. So everything just scaled up by a factor of 3. And we've dilated our shape. So we're going to look at one more thing, is how do I look at an object and verify that it is similar? So I'm going to look at a shape that has been, well, we're not going to say it's been dilated because we don't know it's been dilated until we can verify that. So we're going to say, is this dilated? Or another way of saying that is this shape ABC, is it similar to this shape A prime, B prime, C prime? So we're going to look at these two triangles and ask if they are similar. So just looking at it, they look pretty similar, but we don't know yet. But a good way to test it is do the sides scale up by a consistent factor. So what I mean by that is, let's say we had this side, and this looks about, this side over here, BC, looks about 3 times longer than AB. And you could say the same thing here. A prime, B prime looks about 1/3 of the size of B prime, C prime, or B prime, C prime looks about 3 times the length of this. So there's a way to verify this. And we're just going to take some ratios. So a way to see if this is true is, do the side lengths scale up by a consistent factor? So if I took the ratio of AB to BC, would it be equivalent or equal to the ratio of A prime, B prime over B prime, C prime? So a little bit of math notation here. I'm just going to take the ratio of the side length. So let's take that ratio and find out. So AB with the line over the top just means, what's the length of the segment AB? So here, and then BC with a line over top, it's just the length here. And again, we're just doing this mathematically, what I just described. Is it equivalent to the ratio of this length over this length? So we're just going to verify that, see if it's true. And if it is, we know these are similar shapes. So I'm going to go through and find these. We got the length AB. We'll just count along here. Well, that's a length of 4 units. We got the length BC, we'll count over. We'll count in twos. We got 2, 4, 6, 8, 10, 12. BC is a length of 12. And we're going to ask ourselves, does that equal the ratio of this side over that side? We can see if it's scaled or not. And so right now we made that kind of intuition right at the beginning to say, It's scaled up by a factor of 3, and we can see right here that, well, really, this bottom or long leg is 3 times this short leg here. So let's see if that holds true with the other shape. So A prime, B prime will count across. That's a length of 2. B prime, C prime, we count across. We can count into 2, 4, 6. Length of 6. And it looks like this side length to get to this side length, it's scaling up by 3. So consistent scaling in here. And so we see the consistent scaling, and we can also just verify, are these ratios equivalent? Well, 4/12, so that reduces down to 1/3. So for every 1 unit on the small leg, there is 3 units on the long leg. And well, that's the same thing with this shape down here. It has the exact same scaling on it. So because I verified that the sides scale up by the same consistent factor, I have verified that these are similar triangles. So yes, the sides scale up by a consistent factor. So again, we see all corresponding angles are equal if we look at this. Same, 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 same. And when I say corresponding, I'm talking about the ones that kind of match each other. So these correspond, these correspond, these correspond. They are all equal. And the sides have been scaled up by a proportion, so we got a similar shape. So any questions on this, make sure you save them, bring them to the office hours on Wednesday. So take care. I will see you all later.